We're going to look at what happens when an organolithium or a Grignard reagent reacts as a base, since that is what they're most likely to do. So again, the two different ways that you would see these drawn, you could have the organolithium, or you could have it drawn as a Grignard reagent, or my favorite, and I'm going to use the Grignard since it's more commonly used. You have your carbanion, your cation, in this case the other anion. All three of these could do the same chemistry. Be aware, these are fantastically strong bases, and that's because the corresponding conjugate acids are so weak. So this guy's conjugate acid, if it were to pick up a proton, would be propane. Okay? And hopefully you remember from your pKa charts that your alkanes have pKa's in the mid-60s. I know for methane it's 60, for ethane it's 62, so this is roughly, about 62 for its pKa. That is a weak acid. Therefore, this is a strong. Oops, if I can spell strong. I can't. This one is a strong base. They don't get much better. And the different types of strong bases that you could use in this case, they don't necessarily have to be the conjugate base of an alkane. They could also be the conjugate base of maybe an alkene. These aren't quite as strong, but they are strong. In this case, we would have put the proton back on there. These guys, conjugate acids, would have pKa's in the mid-40s. Okay? So these are commonly used. These are better bases than the deprotonated terminal alkynes that we've used, the alkanides. These are better, and you make these type of bases by doing the organolithium or the Grignard chemistry that we saw previously. So if you are using these in certain types of solvents, you're going to have trouble. Solvents that are no-nos for you. And what you would find is on the bottom, typically, of whatever's on the arrow. There'd be something up top. It doesn't matter right now. But you need to be very careful if you have one of these in solution with either of these types of solvents. In each case, these protons are acidic enough to be removed by this particular base. In the case of the alcohol, the pKa is around 16-ish. For the thiol, that's probably going to be more around 10-ish. And for the amine, that pKa is probably going to be around 36-ish. So any one of these would be, strong enough acids to do favorable acid-base chemistry with this particular base. So for example, let's do the acid reaction. I know this guy has, cations and anions that are potentially associated with it. They're going to be spectators. They may be here, but they're spectators. So what's going to happen is this pair of electrons will come in here, remove the proton, and you'll give electrons back to the oxygen. Sorry. As that occurs, you're going to make propane, and you would make methoxide. Now, I know most of you know methoxide is a strong base, but it's a much weaker base than what we had a moment ago, because the conjugate acid here, propane, has the pKa around 62, whereas methanol, which was the conjugate acid of methoxide, methoxide's conjugate acid is methanol, and that has a pKa around 16. I think it's actually 15.2. So this would be very favorable acid-base chemistry. So you need to be aware of this. If you don't want acid-base chemistry to occur, avoid these types of solvents. Do not use them. And be aware, if you are trying to do some chemistry with another molecule, if you have an acidic proton, you may not do the nucleophilic substitution that you are hoping for. You may be doing acid-base chemistry instead, because these are such strong bases. And you need to be aware of that. You need to remove any acidic protons or do something to protect a group before you do chemistry like this.